Hi everyone, this is going to be a follow-up video to my previous one about VSEPR theory and Lewis structures. So we're going to be talking about intermolecular forces and polarity, which does go right directly with that VSEPR theory that I was talking about before. So the first thing to know, or remember I should say, is the difference between ionic bonding versus covalent bonding. In an ionic bond, if we recall from my last video, electrons are being transferred from the metal to the nonmetal, from the cation to the anion. And that's due to that difference in electronegativity. And with covalent bonding, those electrons are being shared between two nonmetals. They're not always shared equally though, sometimes they're shared unequally. And again, that is because of differences in electronegativity between different atoms, okay? So when you have unequal sharing in a covalent bond, some different things can happen. So let's first talk about what even is an intermolecular force. So we're going to break down this term, intermolecular. The second part of the word should be fairly simple. Molecular refers to molecules. And this prefix inter means between. So I'm going to be talking about the forces between molecules. Specifically, forces that occur between different molecules, not within the same molecule. Between different molecules. So you have one molecule over here, you have one over here. What are the forces that are happening between the two of them? Okay, so there's a few different kinds. There's London dispersion forces, dipole-dipole forces, and ion-dipole interactions, which again, they sound big, they sound fancy. They're not really that complicated. You just have to understand polarity and unequal sharing of electrons. So the first one is a London dispersion force, and that is largely thought of as the weakest intermolecular force, so it's barely there. It is there, but it's very weak. And what it is a temporary force that results when the electrons in adjacent atoms are close enough to one another that they kind of form temporary attractions. So imagine, if you will, and there's an atom over here with some electrons around it, and there's an atom over here with some electrons that are kind of around it, whatever. So when those electrons move into proper positions, there can be attractive forces between different atoms based on the position of their electrons. So those are temporary because electrons are moving all the time. If the electrons move out of the proper position, that attractive force won't be there anymore. So that's what's happening with the London dispersion forces. So here's a slightly better drawing than the one that I just did. So if you see here, let me just break down this drawing real quick. The nucleus of an atom contains protons and neutrons. Protons have a positive charge, so I'm going to draw a big plus here, and I'm going to draw a big plus here. The electrons of atoms, as we recall, are negatively charged, so those are minuses. So what you're seeing here is when the electrons are moving in a certain direction, like you see how they're kind of all hanging out on one side of this atom and one side of that atom, all these negatives here can be attracted to the positive of a different atom. So that negative and positive is going to be attracted to one another temporarily, because again, those electrons are not going to stay there forever, and neither are these. They're going to move back around, and so are these. And as soon as that happens, that temporary positive-negative attraction is immediately destroyed. Like, it's immediately, these electrons get in the way, these move out of position, and that London dispersion force is gone. Okay, so that's why it's the weakest, because it's very temporary and it's weak to begin with, because look how far away that positive is to those negatives anyway. We also have something called a dipole-dipole force, and that is the attractive force between the positive end of one polar molecule and the negative end of a different polar molecule. Okay? So this picture here kind of explains that a little bit. And it might seem confusing at first, but again, I'm going to break it down for you. So once again, we're seeing negative electrons, right? We've got electrons here, we've got electrons here, got electrons here, electrons here, electrons here, electrons here. We also have them over here in this different situation, so I'm just going to go ahead and circle them as well. Okay? Now, with this situation on the left, this one over here, those electrons once again have a negative charge. It's negative, 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 negative. And you might be a little confused right now because you're saying, well, why are those electrons attracted to that hydrogen? Well, think about it, you guys. Hydrogen is made up of one proton and one electron only. And that electron in this hydrogen specifically right here is involved with a bond over there. There's no negative electron over here. The closest electrons to this side of the hydrogen are this oxygen's electrons over there. So those negative electrons are attracted to the positive side of this hydrogen over there. And these electrons here are attracted to the positive side of this hydrogen over there. These electrons here are attracted to this hydrogen right there because that positive is attracted to that negative. And now that's happening between two different molecules, and that's where that attractive force is coming from. Now, the reason that that's even happening to begin with is because of that polarity of this entire water molecule right here. So if we look at what's going on in a water molecule, which I'm just going to doodle over here, we have an oxygen that is bonded to two hydrogens. Okay? So we have a bunch of negative over here because these electrons are here, these electrons are here, electrons are negative. Are there a few protons here? Yes, absolutely. But on the whole, there's a lot of negative on this side of the molecule. We have protons here and here. Yes, there's an electron here. Yes, there's an electron here involved in that bond. But on the whole, most of this molecule, or this side of the molecule, is positive. So you have that polarity, those opposite poles forming. You have your negative pole of the molecule over here, and you have your positive pole of the molecule over there. So that's another reason that that attraction is happening between all these molecules, is because you have negative ends of molecules and positive ends of molecules, and they are attracted to one another. Okay, so that situation with water, that hydrogen being attracted to oxygen and all that, that's referred to as hydrogen bonding. It is a type of dipole-dipole force, but it's not always just with hydrogen and oxygen because of water molecules. It can happen with other situations as well. So hydrogen and oxygen aren't the only two things to ever be attracted to one another. It could be a hydrogen and a chlorine, like in this situation here and here. But it's the same thing, you guys. We have, let me erase a couple of things, actually. Let me erase over here so I can doodle something else. We have over there this carbon, and there's two chlorines, and then there's two hydrogens over on that end. Okay, so that molecule, we have chlorine, which again, there's some positives in the middle of it, but chlorine has valence electrons. There's electrons around it. as you know, because you can draw Lewis structures now too. So look at all those negatives that are here. There's 7 of them. And then the one that's participating in the bond right there. Again, over here, there's 7 of them, including the one that's participating in the bond over there, but 6 on either end. So this chlorine end of that particular molecule is highly negative. And again, we have a water molecule with a hydrogen that's highly positive sticking off over there. So that positive hydrogen is going to be attracted to the negative in the chlorine, and that's what's forming your association. Okay? So to talk about hydrogen bonding just a little bit more, because it is very important, it is largely considered the strongest intermolecular force. It occurs because the hydrogen atoms with your partial positive charge are attracted to your electronegative atoms, mostly oxygen and nitrogen. Okay? This is why water has surface tension. This is why that happens. So that's why it's so important, because it affects us every day. Okay? The third type of intermolecular force is that ion dipole force that I had mentioned earlier. And that's the attractive force that results from an attraction between an ion and a polar molecule that's neutral. So what I mean by that is, let's say that we had water again over here. That's that neutral polar molecule with its negative end and its positive ends. And let's say that floating over somewhere over there, we had a sodium atom that was positive. So this positive is going to be attracted to that negative. And if we had chlorines that were negative over here, they would be attracted towards the positive end of the water molecule. So that's an ion dipole, because we have ions being attracted to a polar molecule. But it's the same idea as your dipole-dipole interactions. So let's talk a little bit more about polarity and why and what the heck. Polarity is an unequal sharing of electrons in bonds that result in molecules having differences of charge on both ends. So those poles that I was talking about, okay? So once again, this electronegativity diagram, once again, to remind everybody, the most electronegative atoms are found over here in this section. The least electronegative atoms are found over there in this section. So that's why we get that sharing of electrons happening when nonmetals bond to nonmetals, because all the nonmetals are relatively electronegative and they kind of play that tug of war over their electrons. Okay? Fluorine is in fact the one that I circled here really, really heavily. That is in fact the highest electronegativity on the periodic table. Okay, so we have unequal sharing happening because of that difference in electronegativity. So in a water molecule, again, water is going to be a very popular example in this class. Oxygen is more electronegative than hydrogen, meaning oxygen is stronger in the tug of war. It can pull electrons much better than hydrogen can. So all the electrons in that bond are going to spend most of their time hanging out with oxygen. They're going to spend a little bit of time around hydrogen, like a little bit, but most of the time, those electrons are going to be attracted to oxygen and hang out around there. Because remember, electrons are moving all over the place all the time. So an electron might start out here and it might go woo, and it's going to move around and kind of going to circle this, and then it's going to circle around and hang around oxygen some more a bunch, and then it might deviate and kind of circle this hydrogen, but most of the time it's going to hang out around oxygen, and then it might kind of go back to this hydrogen, but again, it's going to circle oxygen a lot, and then, so you see how messy it gets when I'm tracing the orbit, but that electron spent much more time hanging out with oxygen than it did with hydrogen in this little fun drawing that I just did. Okay, and that's because oxygen is an electron hog. all right? So that's why you're getting that overall positive charge on this end and the overall negative charge on that end. This little funny looking S that you'll see me draw in class, that is used to denote electronegativity. So if you ever see, or polarity, I should say, if you ever see this is me telling you that this is the negative end of a molecule. If you see this is me telling you that that end of a molecule is positive. And the reason that we use this rather than just straight negative or positive is because these are used to denote an overall charge for an entire molecule. So if I said, or for an entire atom, so if I said Na plus, that entire sodium atom has a positive charge, versus this is a molecule and one end is slightly negative and one end is slightly positive, but overall that entire molecule is neutral. So that's why we use something else. But why do we care? Because polar molecules interact with the things that they come into contact with, which is like everything. So any molecule will interact with any other molecule that it comes across. And so that creates a lot of things that can happen between water molecules and other water molecules, or water molecules and other molecules, or you and your neighbor, or you and a desk, or whatever. But that's why things happen in the world the way they do, because of molecular polarity and because of intermolecular forces. So I just wanted to really quickly highlight the special properties of water that exist because of hydrogen bonding. Water is cohesive, which means it's attracted to itself. So when you pour water on a surface, it forms droplets, rather than spreading out on a surface. Which is why surface tension is a thing. Again, water interacts and bonds and is closely associated with itself. So if you've ever seen that Mythbusters episode where they were testing if you could save yourself falling from a high space into water by dropping a hammer, and that failed, it's because of the surface tension of water. Because if anybody who's done a belly flop into a pool knows this, but if you fall on water, it stings. If you fall into water from a high enough place, it's like falling into a brick wall. Even though we can swim in water and move through it, that surface tension causes some problems. Okay? Water is able to dissolve ionic substances and some covalent substances because it is polar. So that's why you can dissolve salt in water. That's why you can dissolve sugar in water, because water is polar and it's able to pull those salt and sugar molecules apart. And that's very important for chemical reactions that happen in your body. So this is a water strider if you've ever seen one. The reason it can stride or walk on water is because of water's surface tension. And here's a nice graphic of water interacting with sodium and chloride ions. So this over here is salt that somebody dropped in water. So this is salt crystals. What the water is doing, because of those positive and negative ends on it, is it is pulling that molecule apart. It's pulling off chlorine ions and sodium ions because of that polarity. So this is just a nicer visual as to what happens when you're dissolving substances in water. So once again, I'm going to talk in class more about the Vesper chart and how to determine molecular shape based on what's in a molecule and everything like that. But I hope that this was clear enough and helpful enough so that you can understand what's happening between molecules. Have a nice day.